middle saying, two different people within 24 hours pinged me as with this paper from Thomas Roberts as a rebuttal and a contention to Miller's works. So I decided I better look into it. And like immediately, as soon as I started looking into it, the tone and premise of the paper, to me, was essentially just gaslighting Dayton Miller for not having a digital computer 100 years ago to do his own analysis. Essentially, the paper says that he didn't have the ability to do a proper Fourier transform to get a proper amount of error bars. Um, and so I was tempted originally to make this presentation kind of snarky for numerous reasons. I mean, the paper attacks Miller's second order math as applied to his first order measurements or derived from his first order measurements. And that's not, where I would say the significance is found. The significance is found in the first order measurements. The second order analysis is an attempt to correlate the first order measurements to an absolute motion of the Earth. But geocentrists, like me, we don't assert that. So, his second order analysis, picking that apart, is not really relevant to us. We don't have, and another thing, we don't have open access to Miller's original measurements, which makes the whole thing pretty confusing and frustrating. The last people to receive this data, to my knowledge, were James DeMayo and Thomas Roberts. So it's difficult to know how meaningful any of the analysis, is to an extent. And we're forced to rely on the analysis of others. Historically, and looking at the different analyses that were brought forth meaningfully, we're forced to look at those. And Miller systematically always addressed the critiques of his work in real time over the years. So in the Thomas Roberts paper, when we get into it, you'll see he takes a selection of data chosen to analyze, and it's essentially done at random. He picks certain a lot of the data sets he throws out because the drift was too large. So he throws out anything that had too much drift, even though Dayton Miller claimed that the periodicity was always present even with the drift. But when Thomas Roberts does a Fourier transform and takes the error bars down, he claims that those can't be used. But with anyways, a selection chosen to analyze of Miller's work, in my opinion, really shouldn't be done randomly, because Miller published all of his works, everything, even the bunk stuff, to be transparent. But to properly analyze his data, you really need to know the origins of it, and you need to take those things into account, which I did not see happen at all in the Thomas Roberts paper. And no one really knew the origins of Miller's work better than Miller himself. So although I don't really put too much weight into his second order analysis, the guy was basically the grandfather of interferometry to an extent, right? Like, he's the one that really put the time in and tested things. So I kind of trust that the dude had a feel for what was going on, what he was measuring, and the periodicity that he was seeing. 5 million, over 5 million data points. Yeah. So let's get into it. So we're calling this Recomputing the Ether. It's a look into various analyses of Dayton Miller's experiments. So we're going to do a brief history real quick, which I know is quite redundant, but it doesn't hurt for us all to become intimately familiar with the history of electromagnetic wave measurements. We're going to take a quick look at Miller's work, and then we're going to take a quick look at his own analysis of his work. We'll take a really quick look at some analysis by James DeMayo, and then we'll do a look at the Thomas Roberts paper. And I think it's important to set it all up for the Thomas Roberts paper, because if we just jump into the Thomas Roberts paper without any context, it's not gonna be as meaningful. And then after that we'll go back to Yuri Galev, and we'll look at his analysis and corroborative results. But also, I'm not going to mention Sagnac, who measured similar things, which would have corroborated Miller. At least that's alleged, or has been mentioned in some texts. Monera corroborated Miller's periodicity, but had his own second-order measurements. Elias did his own analysis of Miller and corroborated Miller. Other people that have done analysis on this work are Soleri, Cahill, Consoli, Dean, Sato. So there's a lot of other analysis of this out there, but this is what we're going to focus on for today. So yeah, going through the history really quick of how we even got to the point where they tried to measure the quote-unquote absolute motion of the Earth. We go back to 1831. People, Fresnel started making theories about an ether drag, the concept of light being dragged by a material medium. In this case, water. There's a 44% proportional velocity. So in here, right here, we have the sunlight shining in, gets split by this mirror, goes down, and then on this, so as this light wave gets split, this half of the wave is going to go down. It's going to go with the water. And then this half of the wave is going to go against the water. And so then when that light wave recombines, you get what's called a fringe shift, because you can see the difference in how long it took those two different waves to get to the detector. And so you can look at that fringe shift to see to see if this formula that Fresnel came up with in 1831 was indeed correct. And in 1851, Fizeau did exactly that. He did this exact test and found that Fresnel was indeed right. 44% proportional velocity. There's also a 70% refraction rate. The induction of the light or the excitation of the light is slowed down by about 70%. But then, like I said, there's the 44% slower this way and 44% faster this way, thanks to the ether drag of the material medium of the water carrying the light. So then in 1865, J.C. Maxwell put a lot of these concepts to math, and he used known values of the electric constant and the magnetic constant in his electromagnetic wave equations, and that he, really helped us figure out the fact that light is indeed electromagnetic waves. So they understood very well at this point what was going on. They understood that light was being inducted into by a material medium. So that was the premise for interferometry. And interferometers work by, as I was kind of describing earlier with the Fresnel drag, that they work by splitting a light beam into two, shooting them orthogonal to each other, and then before reflecting back and recombining, if there's any difference in that speed that they travel, the induction rate, there's going to be an interference pattern which can be measured and analyzed. So in 1887, they came along. Michelson and Morley came up with the experiment to do a test to use this premise to measure the quote-unquote absolute motion of the Earth. And the dependent variable would have been c, or the speed of light, quote-unquote, and the independent variable would have been the orthogonal vector direction, because essentially you could just turn the interferometer and observe the difference in the fringe shift depending on the vector that the two different orthogonal vectors and how that fringe shift was being produced by that. And what they found was not the Copernican principle. They expected to measure a orbital motion of the Earth, because at the time they still believed in a material medium necessary for electromagnetic waves propagation, which is what light would be. So they expect to see 30 kilometers a second, and what they saw was closer to 3. The interferometer wasn't really designed to be precise enough to measure down that low, but it did not make any sense with what they expected and with the expectation of the Copernican principle of the heliocentric model. So, but the result could be explained pretty easily with a stationary Earth and an ether wind. But in 1905, Albert Einstein came along, and he brought his principle of relativity to the status of a postulate, and he decided that, we're going to get rid of the ether, and there's going to be, no absolutely stationary space anymore, and we're going to invoke an imaginary physical experiment, and what do you know? Speed of light's speed of light's constant. So when the speed of light's constant, it's the only way you can throw out the medium that electromagnetic waves propagate through, right? So they now just basically broke physics, and they made a cheat code to get rid of the material medium. And they said that the Michelson-Morley experiment just didn't. What it measured was an instrumental error, and it was actually just no result. It was null. There was no motion measured at all, right? And that's that. Speed of light's constant. You can't measure the motion of the Earth. Everything contracts in relation to the sun, so good luck. good game. We're done. No motion can be measured, but trust us, it's in motion. So enter Dayton Miller. Miller thought there was probably more to it than that, right? So in Cleveland, Ohio in the 1900s, he started doing his own first order measurements. He started learning he took the same design as the Michelson-Morley interferometer and started doing his own adjustments to it. He added more mirrors to make it more sensitive, and he just started measuring. He started learning it, and it was his first model was wooden. But as he was going, he started learning the variables, and people would criticize his works, his measurements, say, hey, you're not accounting for temperature, so he would account for temperature. People would say, hey, you're not accounting for pressure fluctuations, so he would account for pressure fluctuations. And every time, not only would he account for it, but he would test for it. He would induce the temperature changes, the pressure fluctuations, the vibrations, and he would see how big of a difference was made on the fringe shift reading from these different things, right? And so he understood what was going on really well with that, and that allowed him to better account for these different variables when he was trying to take meaningful measurements. And the average speed that he observed, the absolute motion, quote unquote, was around 6 kilometers per second in Cleveland. And he observed a periodicity, or he thought he was observing possibly a periodicity at that time. And he started to note that metal shielding affects the readings. And then in the 1920s, because of what his inklings, what he had ascertained so far about these readings, he thought he needed to get up to altitude. He thought the readings would be more pronounced at altitude. So he went to the Mount Wilson Observatory in California, and he took hundreds of thousands of measurements. And he found there an average speed of 8 or 9 kilometers per second. And he did more testing with steel and concrete interferometers and further, solidified his stance that the metal shielding degraded the signal. And he observed much more intimately on a much more grand scale, the periodicity. And here he is with Albert Michelson at a conference about the MMX experiment, interestingly held at the Mount Wilson Observatory in February 1927. And here he is with his flute. And interestingly, Dayton Miller had a massive flute collection. He was an acoustician by trade, and he understood the etheric background. And if you think about it, an acoustician would understand the etheric background better than anybody, because you can't conceptualize. If you're an acoustician, you're not out there conceptualizing of a bunch of particles bouncing into each other, right? That's not what the free space is. That's not what the sound waves are traveling through. No, they're traveling through a fluid background. They're traveling through an ether. And so that's, I believe, a big part of why Miller was so sure of the fact that there had to have been a material medium for things to propagate through. And so in 1925, he says, this is him talking about his measurements, the direction of the indicated motion is fixed with relation to sidereal time. That is, it is towards a fixed point in space, as a motion of the solar system towards the point having a right ascension of 17 hours and a declination of 68 degrees north. Ether drift produces an effect as observed in the interferometer, which is proportional to the square of the ratio of the velocity in the cosmic motion of the Earth and the velocity of light. This is a second-order effect and is periodic in each half revolution of the interferometer. The complete theory of this experiment shows that there is necessarily also present a first-order effect periodic in each full turn of the interferometer. And so here he is, him showing one of his earlier analysis showing the alignment, the correlation to sidereal time with his measurements. And he says, observations at different sidereal times show that different azimuths, and all observations at the same sidereal time should show the same azimuth. 35 sets made on different days, 11 sets at different sidereal times. There is a definite relation, some definite direction and velocity of ether drift. So that was his position at the time. And here is his own analysis showing the sidereal time relationships. And so this is his general program of observation. The ether drift observations made by the writer previous to 1925 consist of 25 sets of 995 turns made in a collaboration with Professor Morley in 1902 to 1905, 86 sets of 1,146 turns made in Cleveland in 1922 to 1924, and 166 sets of 1,181 turns made at Mount Wilson in 1921 and 1924. These experiments had given conclusive evidence of a real effect which was systematic, but was small in magnitude and was inexplicable as to its azimuth. A program was adopted involving an extensive set of observations for the solution of the general problem of ether drift without any presumed effects. Since the orbital motion is always tangent to the orbit, it will have different directions at different seasons, producing a resultant absolute motion peculiar to each epoch. The number of sets of observations for these epochs is 36, 96, 83, or 96, 83, and 101, respectively, giving a total of 6,402 turns. So this is him seeing periodicity in multiple sets of his data, his own data that he understood probably better than anyone else. But, you know, in 1933, he released a book, and he had his own second-order analysis of all this data, which I have never heard any of us bring any of this up. Ralph on Twitter, shout out Ralph, brings this up. He loves talking about Miller's second-order analysis and Demio's second-order analysis, but no geocentrist cares about this. We care about the first-order measurements. But just to show, Miller was indeed a heliocentrist. And this is his model illustrating the positions of the Earth in its orbit at the 4 epochs of observation. Isn't that fun? And then here's this interesting picture, right? The chart of observed apexes to the resultant absolute motion of the Earth. And it's basically showing the way that in which the ether drift would have to be moving in relation to the Earth's motion. And his theory is essentially that the Earth would be in motion, and along with the Earth's motion, there's also an ether wind. And somehow these things move together in a way in which we can measure the motion of the sky and the sun and the moon. That's, you know, the first order measurements. If you apply a second level abstraction or second order abstraction, you can make it kind of work. You can draw some correlations, but you have to get into some interesting motions. But yeah, so there you go. That's Miller's. Here's some more of his own analysis. The point on the celestial sphere towards which the Earth is moving because of its absolute motion is called the apex of its motion. The theoretical consideration of the determination of the apex of the motion of the Earth has been given in a paper by Professor J.J. Nassau and Professor P.M. Morse, which appeared in the Astrophysical Journal for March 1927. Knowing the latitude of the observatory and the sidereal time of the observation, 2 independent determinations may be obtained for the right ascension and the declination of the apex of the Earth's absolute motion. One determination from the absolute velocity and one from the azimuth of the ether drift effect. The ether drift effect being a second-order effect. So here he is doing a harmonic analysis, whatever that is, crazy acoustician, right? The harmonic analysis of the observation gives directly the, and I know it's probably a real thing, I'm just making a joke, of a fringe width and the phase as referred to the north point of the second harmonic of the curve, which is the ether drift effect. The observed amplitude of the movement of the fringes is at 1 converted into the equivalent velocity of the relative motion of the Earth and ether as observed in the plane of the interferometer. And then here it is. I gotta say, I like the dude's handwriting a lot. But yeah. So, that was his analysis. That was Miller's analysis. The first order stuff, the first order measurements, boy oh boy, I wish we could get our hands on that data. But, you know, it's out there somewhere. But this is his second order analysis, right? And I'm just really quickly going to double check that things are looking good with my stream. I guess it's kind of late to do that, really. Yeah, anyways. So this is now James DeMayo's analysis. This is just I just grabbed a couple of screenshots from his paper. So he found his own relation with sidereal time and civil time, or really he just looked at Miller's analysis and then kind of reanalyzed Miller's analysis and drew his own lines of logic of why he thought Miller's analysis was good. And he talks about how Miller did later on recompute his periodicity. And While Miller's 1933 paper assumed the Earth was pushing through the ether and moving towards Dorado near the southern pole of the plane of the ecliptic, the movement and direction of the ether drift past the interferometer was exactly the opposite to this. It is important from the standpoint of his working theory to clarify the concepts of the net motion of the Earth versus the direction of the ether drift. Wow, it's almost like when you just try to ignore the fact that it's the sky moving and the Earth is stationary, that it gets really complicated, and these guys all have to start arguing with each other and making up like crazy, nonsensical, and uncanonized stories to try and make things make sense, because they have to have the ground beneath their feet be moving for some reason philosophically.
Nice.
So now let me just drop down here. So that's all I have for the presentation, but now we're going to jump right in to the Roberts paper. So this is an explanation of Dayton Miller's anomalous ether drift result. The result is in direct conflict with the prediction of special relativity. We can't have that. All right, I promise I wouldn't. Sorry, I promised myself I wasn't going to be snarky. No such signal of absolute motion. I'm going to be snarky. That's all there is to it. His results are not statistically significant. Flaws in his analysis procedure produced a false signal with precisely the properties he expected. What a poor
5 million
dupe.
times.
Poor dupe. Upper limit of absolute motion of 6 kilometers per second is derived from his raw data, and it's fully consistent with similar experimental results and the prediction of special relativity. So, like, he had a false signal, his results are not significant, blah, 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 but it's fully consistent with what relativity predicts, so we're all good. Comprehensive and qualitative error analysis. The concepts and techniques used in this analysis were not available in Miller's day, but are now standard. These problems also apply to the famous measurements of Michelson and Morley and to most, if not all, similar experiments. So Thomas Roberts is going to school Michelson and Morley and Miller and everybody, and Elias and Cahill and Kiddo and Const. He's going to school all these people. So Dayton Miller's article was published in the Modern Physics Review, and Shanklin in 1955 attempted to address the situation by re-examining Miller's data, but did not give any argument or discussion of how that could generate such a remarkable result. So interestingly, Shanklin didn't even look at the Mount Wilson data, which is the most significant data, but he doesn't even mention that here. Noise in the apparatus. Yeah, so he said that Miller found noise in the apparatus that perfectly mimic the signature of a real signal. So, reasons to reject Miller's claim. A basic error analysis of his results show that they are not significantly significant. And analysis algorithm has serious flaws that force the noise in his data to precisely mimic the properties he expected in a real signal. What a coincidence. And a quantitative, which, by the way, we just looked at him himself saying that he wasn't looking for a signal. He found the signal by doing objective analysis. So that right there is already like, wow, good way to gaslight the dude that's been dead for 80 years. A quantitative model of his systematic drift accounts for 100% of his usable data, leaving no real signal. No real signal, not an ounce. Can't have a drip of it. The real analysis of his data puts an upper limit of 6 kilometers per second on the absolute motion of the Earth, which is fully consistent with the related experiments and the prediction of special relativity. The authors contented themselves with merely claiming an upper bound on any signal, such as upper bounds. Such upper bounds remain valid, and this analysis explains why these upper bounds are larger than their observational resolution would suggest. So he's talking about upper error bounds, essentially. And honestly, I'll be totally straight. Like, he essentially ends up doing a Fourier transform on Miller's data, and I have a loose understanding of how Fourier transform works. It's essentially it's actually a pretty straightforward way to quote unquote do a digital signal processing. And like now, if you were trying to filter through some sound, like if you were playing music, you could use a Fourier transform and find the aberrations from the sound waves quite easily and tune those out, just given the nature of a Fourier transform. And digital signal processing, especially, given a digital signal, why wouldn't you use digital signal processing? Now, the thing is, this was not, initially a digital signal. Granted, it is essentially digitized when it's put to pen and paper in the form of numbers, and that's done by looking at fringes by Miller's assistant. Which honestly, this assistant did so much, I feel like I should know their name. But in any case, the key point of the paper is the importance of error bars. Well known today, but not common in Miller's day. Dude just didn't know. Poor guy. If he only had a Windows PC with at least, Windows 95 on it, he could have done the math. But back then, pen and paper, nope. So there are 16 markers. Let me just skim through here. I don't think we want to read the whole paper because it's just a lot of analysis. So he claims a system. So what data are we looking at here? I notice he does a thing here. He starts talking about all of his judgments, right? He starts making all of his points. But he doesn't even tell you what data he's looking at until... Still hasn't told us, I don't think. Eventually he does. Maybe I missed it. Oh, here we go. It's been applied to a sample consisting of 67 of Miller's original data runs, which we know Miller did a heck of a lot more than 67 runs. But at least he grabbed from 25, 27, 29, and the Mount Wilson data. So at least you got to grant him that much, right? So basically, he cherry picks 67 of Miller's original data runs, specifically cherry picks 67 that had the least amount of drift, which, like I said earlier, he's not the guy that took the measurements. So, Miller published everything. That doesn't mean necessarily that everything is good data. So this guy grabbed 67 of them that he thought were the best, and then he did his analysis based on that. So let's see here. He says right here, this analysis cannot really determine the direction of an absolute motion at all and cannot say very much about the speed other than that it is less than 30 kilometers per second. So, I don't know. It's just funny that he says it's perfectly consistent with relativity, but then he says that too. Like, which one is it, buddy? Had he computed and plotted error bars as above, they would be so large that in no case would they fit on the plot, and often would not even fit on the page. You don't even have enough paper, Mr. Miller. Stop trying, buddy. Maybe give us 100 years. In 100 years, we'll come and tell you why it's all relativistic. Don't worry. There's no point in actually performing a detailed statistical analysis from this analysis method. Cool. So, and then he starts talking about the Miller's harmonic analysis. Using this data reduction algorithm, any noise with a failing spectrum will end up looking like an approximately sinusoidal signal with a period of half turn, precisely what Miller was looking for, stupid acoustician. One needs to do a more sophisticated analysis to determine that, courtesy of Bill Gates. Together with his rather large systematic drift, they permitted Miller to be fooled into thinking there is a real signal present. Poor guy, just a victim. It's not surprising that he was fooled. So this is now his reanalysis of Miller's data. And he says, yeah, so any real signal has been removed from the plot. That's via the Fourier transform. He does the Fourier transform, removes everything that's not, expected, essentially. I mean, it reminds me kind of the way they do the Elias effect measurements, right? They put a pendulum in, and then they put that pendulum on some guardrails via an electromagnetic break and an oscillation rate that is consistent with the expected outcome, and it's designed to not deviate from that expected outcome, And then what do you know? You get the expected outcome, no Elias effect, relativity confirmed. Which to me, that's what it feels like when you're throwing a Fourier transform on Miller's data. But maybe we can get a more thorough explanation on this from somebody. I don't know. I don't care that much because, like I said, it's the first order measurements that we care about. We don't even care about Miller's analysis. But in any case, permitting each sequence of figure 10 to move vertically independent of the others and to fit the term to avoid the usual normalization ambiguity in such a fit, the first parameter is fixed by requiring the model to match the first data point. Data are quantized at 0.1 fringe. Instead of the usual minimization programs, an enumeration of all reasonable sets of parameters was used with an algorithm that finds the minimum x squared. The result of the fit is a complete quantitative model of the systematic time for the run. Fitting each run took about 3 minutes of computer time to enumerate several million combinations of the 7 parameters to find both the best fit and the error bar. You could never have done that with your little pen and paper, Dayton Miller. So eat that. Math wins. This analysis has been applied to a sample consisting of 67 of Miller's original. Yeah, we already read that. Figure 11 shows minus systematic. The variation due to the rotation of the Earth is negligible because during a run it is less than 6% of the angle between markers, and corresponds to a timing error that is smaller than the reaction time of the human observer. This rotation is mostly in the plane of the interferometer. It is reasonable, of course, it is reasonable to admit all runs with instabilities during 3/4 of the run, as a systematic model can be expected to model instabilities very well. So, just don't worry. Let's just throw some more data out. Non-zero Fourier amplitude with period half turn come from several data, which simply means the instrument had periods of instability that lasted longer than a single run. So somehow magically the instability is just always there, and it's conveniently always, just throw it out. Because, every run that's not what we want, we don't need to look at. The conclusion is that during these runs, the interferometer was just too unstable for systematic drift to be modeled well. Without an accurate model of the systematic drift, any analysis is useless. It's poor old dumb old Dayton Miller, especially for runs during which the systematic drift was exceptionally large or ill-behaved. So these 14 runs have been omitted for further analysis. As a systematic model reproduces the data exactly for these runs, the uncertainty in the systematic fit gives the complete error bar for this analysis. It inherently includes both systematic and statistical errors. So, as this analysis concludes there is no signal in Miller's data, it can set an upper limit on any signal with a period half turn and on the absolute motion of the Earth. The value is consistent with similar experimental measurements and with the null result predicted by special relativity. Dayton Miller was a prisoner of his time. In the 1920s and 30s, they didn't have a Windows computer like you do there at home. They couldn't just push Windows key R and pull up the calculator. They couldn't program it on a terminal screen like I can, Thomas Roberts. And the flaws of his data reduction algorithm went unnoticed because none of those guys had Windows computers that they could boot up and run through an algorithm without, pen and paper. So he got fooled into thinking his interferometer measurements did indeed determine the absolute motion of the Earth. Shanklin did not have knowledge of these aspects of Miller's analysis. So even though we're still going to invoke Shanklin, like the same people are still going to invoke Shanklin to discredit Miller, they're also going to invoke this guy, Thomas Roberts. I guarantee you're going to find people who are going to invoke both of these papers, even though this guy is basically telling you how useless Shanklin's analysis was. It's kind of funny, right? So anyways, today, of course, digital signal processing is well known. Digital computers are ubiquitous, and quantitative error analyses are presented in essentially all scientific publications. Applications of now standard techniques to his rather ancient data. Poor Miller. How could someone as competent as by the way, if you're just listening or something, I'm reading right now. So here we go. How could someone as competent as Dayton Miller obtain results so inconsistent with other experiments? Couldn't possibly be anything related to the metal shielding that he brought up. A victim of every experimenter nightmare, he was unknowingly looking at statistically insignificant patterns in his systematic drift that mimicked the appearance of a real signal. No significant signal in his data. And we've got a 90% confidence on that. 6 kilometers per second, null result, fully consistent with similar measurements in special relativity. But man, give the guy a break. We are all prisoners of our time. While this paper gives solid and credible reasons to reject Miller's result, which, by the way, none of us are out here bringing Miller's result. We're bringing the measurements. Ha! Isn't that funny? We're not talking about any of this. But whatever, Blitz PhD dropped this on our lap. Cool. Or whoever else dropped this. I can't even remember who the other person was that dropped this on me. It's funny, though, how 2 people dropped it on me within like 12 hours of each other. It's like there's like some team out there or something. But maybe it's coincidence. Maybe it's in the ether or something. But anyways, recognizing that he could not possibly have known about these flaws in his results permits us to admire him, and all more for his dedication and perseverance in pursuing these measurements. He might have been wrong, but it was a good effort. So there you go. There's the Roberts explanation. I was extremely snarky, but that's the way it's going to go sometimes, I guess. I'm going to work on that.
Dude, that was good. But yeah, the whole thing is snarky. So you read it, and that tone, I think, perfectly embodies his actual,
Good.
position and what he was trying to do, right? But it should be noted for anyone trying to discredit us that, we can prove the same with 0 Dayton Miller, 0 Bob, 0 any of the stuff that you've been trained to refute. Just throwing it out there. We have much, much, much more evidence of all the same.
Yep. And so just really quick, I want to end actually on Yuri Galev, because as I was pointing out, there's analysis that's been done, and we can analyze and try and make some kind of framework for how the ether drift is actually a measure of the absolute motion of the Earth. We can try and do some crazy second layer abstraction to make that work. But I don't care. I want to get back to the first order measurements. So even though Yuri Galev even does a little bit of his own second order stuff, he most importantly corroborates Miller's first order measurements. And also absent from the Thomas Roberts paper is the, just actually like blatantly absent from the paper was the differences at altitude. The 6 kilometers per second at Cleveland, Ohio versus the 11 kilometers per second, or 9 kilometers. It depends on which algorithm you use, or which analysis you look at, but it's between 9 and 11. It's around 6 in Cleveland, and then 6 to 7 in Cleveland, and then it's between 9 and 11 in Mount Wilson, at the Mount Wilson Observatory. So that is what Miller had found with first order measurements, and then in 2001, this is one we want to look at first. Yuri Galev came along and said, "Let's take a peek," and so he actually goes into pretty great detail about Miller's works, and he talks about the ethereal wind speed at Cleveland. And so, here he says Cleveland was 3 kilometers per second and Mount Wilson was 10 kilometers per second. So pretty massive difference there. But so he says, all attempts in order to repeat Miller's experiment, except the experiment, were performed by devices which were placed in metallic chambers, just like Miller said. And so every time they keep getting these 0 results, but they're always in metallic chambers. There was it was done in an air balloon at one point, but this one he's mentioning here was in a metallic chamber again. But we actually do have now we have found a measurement that was done in a balloon that was not in a metallic chamber, and it measures a massive fringe shift. But I will have to get back to that later. In 1929, or Alan, well, I think maybe are you going to bring that up on Tuesday, Alan? If you're there.
Yeah, I sure can.
Cool. So Alan might mention that on Tuesday. But in any case, in 1929, the work by Michelson, Pease, and Pearson appeared, and They found no more than 1/50th of the expected measured. So anyways, in other words, the speed of relative motion of the value of 6 kilometers per second was measured. That's what they keep getting around there. So the Fermi surface thing, Miller figured out something was going on with the metallic chambers, and then Galev specifically figured out its Fermi surfaces. So that's not just metallic chambers, but also dielectric insulators. Both of these shieldings of interferometers greatly reduce any ether wind measurements. So somehow Miller figured that out back in the 1920s, which is actually really cool and impressive when you think about it. But then, especially when it's also cool that Galev figured it out because everyone else has tried to bury this information. But in any case, proper checks of Miller's experiments weren't conducted yet until nowadays. All his followers carefully screened the devices from an ethereal wind by metal chambers. Yeah, so we'll get into that a lot more when we go into this paper. But so in this paper, the main thing that's being measured here is the gradient boundary layer is formed at mutual motion of the solar system and ether near the Earth's surface, in which the ether running speed, ethereal wind, increases with an altitude. The ethereal wind apex is northern. It is shown that metals have larger ether dynamic resistance and interfere with the ether flows. Therefore, metering devices arrangement in metal chambers is inadmissible. But Earth and solar system motion in space availability is not enough to make a conclusion about ether existence, according to him. I don't know why I had highlighted that, because it's missing some context. So he's talking about the modern imagination. Well, interesting. So, yeah. So Sanyak. This is Georgia Sanyak. This is just a weird translation from Ukrainian or Russian rather. Known order effect and relative motion. Miller placed the interferometer at different altitudes and obtained that the speed of the discovered motion raised with the altitude increased over the Earth's surface. So, all this is to say that they say that what they measured here. I haven't even gotten into this because my point here was to dismantle this Thomas Roberts paper and these second order abstractions and these Fourier transforms. We're not gonna give Miller up, because especially not without seeing the data. We want the data, but in any case, this is all very important because there's two things here. They say that this thing that we measure, is the rotation of the Earth. They put in Michelson, Gale, Pearson in 1925, and they measured this exact same thing, and they called it Earth rotation, and they still call it Earth rotation. And they have another setup in Germany, and they tilt it a little bit, and they call it measuring the Earth's precession. But they use they use this measurement to say it's Earth rotation. They call it Coriolis effect and blah 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 blah. But in any case, Miller found the periodicity, which we talked about a little bit already, actually a lot, but I didn't really go into detail what that is, which is that as the sun, so there's a daily periodicity that throughout the course of the day, the quote-unquote speed of light, the preferred directionality of the speed of light increases and decreases throughout the day. And actually, we'll get into that a little bit more in a second. And then also, there's an equinox correlation. So as the sun and the moon move back and forth, or specifically the sun in this case, in this particular analysis and measurement, although there may be a correlation with the moon as well, I think. But in any case, there's an equinox relation. So as the sun's moving back and forth on its analemma or whatever, it's actually causing that interferometer preferred directionality measurement of the speed of light to fluctuate with the equinoxes, meeting its minimum and maximum in correlation with that. And in this paper, it's in here somewhere, I believe. Give me just 1 second while I find it. Because what's really crazy when you get into that thing with the equinoxes is that essentially where is it? I apologize for not having this picked out sooner. I kind of ran out of time preparing for this. Um, but essentially, you get a 30%, like 20 to 30% difference just going from different equinoxes. Which it's like obviously the Earth's not rotating faster at one time of the year than the other. Um, but I fortunately can't find where he did that. Maybe it's the other paper.
Yeah, I think it might be in the other one.
I think it's this one, honestly. Oh.
But yeah, either way, his analysis was that, the fluctuations between the minimum and maximum dimensions, the translational speed there would be like 3,000 miles per hour. So,
Yep.
And like obviously they're going to say, oh, well, you can't measure translational speed, so we only have this angular rotation of 15 degrees. But like the reason they don't want nothing to do with that translational speed is because they need a very specific translational speed for their belief system, and this is way outside the confines of that on the first order measurement of it. And like the significance of that is that with the first order, you can draw that means that you can draw a direct correlation with what's being referenced, right? So with these equations that they're using, where it's like v over c, right? So the velocity components, it's a direct relationship to the speed of light that they're deriving. Like the missing component that they're filling in is the velocity. I'm sorry, that they get out of that fringe shift measurement is the velocity.
Yeah. So I can't find it in this paper at the moment, but in any case, what he did a few different things in this paper. So he talked about Miller, like we showed, and then he did his own experiment. He essentially had radio wave transceivers down here, and then he sent millimetric radio waves here down across these paths, and then the transceivers stayed in operation, and the light propagation stayed in or the millimetric radio wave propagation stayed in operation over a period of time. And so then as the ether wind fluctuations occurred, as the ether wind fluctuations occurred, that was recorded in the transceivers transceivers, and then he was able to do calculations based upon the differences in the altitude, the amount of time at the different altitudes, essentially, and the amount of distance traveled at each altitude between the different paths, to then do calculations for finding the gradient of fluctuation at altitude, essentially. And what he found was that it matched with the expected results of Cleveland compared to Mount Wilson. So here we go. We've got, this is Mount Wilson, and this is Cleveland, and then this is Kharkov, I believe. So 8,000. Shoot, WMK. Horizontal component of ethereal wind in the geographic latitude. So that's Kharkov. So it's this is the altitude differentiation at Kharkov. So it corroborates essentially what Miller had found. So he corroborates Miller's altitude fluctuations, but then he does some pretty crazy analysis of his own periodic effect. And so this is like, man, I'm glad we're getting to this, because I didn't even think about this when I was going through the Thomas Roberts paper, but This is what Miller understood that Thomas Roberts and his Fourier transform and his supercomputer just don't get, is that this drift here maintains periodic effects. We can see it with our own eyeballs. You know, we're not going to let Thomas Roberts gaslight us on this. Oh yeah, oh that's just part of the error. It just matches, but that's an error. No. Miller understood the periodicity remains. Maurice Elias understood with his own pendulum precession, that the periodicity remains. You can have drift, but the periodicity is there. And you can see it. We can see it with our own eyes right here. Thank you, Yuri Galev, for showing us that the drift is independent of the periodicity. So you can squeeze it into your Fourier transform or whatever, but like you're not proper. I have a feeling that maybe you're not tuning your Fourier transform properly. That might actually be what you're doing wrong, because there is a periodicity that your Fourier transform should actually be finding. But in any case, so that's that. But another crazy thing that Galev did in this paper is matching the yearly periodicity. So where are we? Where are we? It's in here. I know it is. Oh, maybe not. Is it that chart up there? It must be the other paper. Although I'm surprised if it is, and I just didn't even remember that. Oh, yeah, here it is. Okay, so this here is Dayton Miller. This is August 16th, I believe, or 18th. Or here we go. I don't know. August epic. So this is sometime in August, Dayton Miller. And then this is 1998 in Kharkov. And this is 2001 in Kharkov in August. So August 11th and August 14th. And we'll look at this. There's a matched periodicity. I mean, it's like 75 years later, and we're still seeing like a similar periodicity with a totally different interferometer. It's incredible. But, you know, let's just Fourier transform all that out of there. So I find that insanely fascinating, that the preferred directionality propagation rate of light, the level of that preference is it fluctuates at a consistent rate throughout the years. That's crazy. But then so that's one thing that's pretty crazy and impressive. But I think that's pretty much everything I wanted to cover around about the periodicity. But let's also one other way in which. So there's the altitude, the periodicity, and actually let's just go through it all while we're in the paper. This is one of my favorite breakdowns of what ether does, is right here, the measuring method. So anisotropy effect. That is, the velocity of electromagnetic waves propagation depends on radiation direction. That is stipulated by the relative movement of the solar system and the ether, the medium responsible for electromagnetic waves propagation. Notice he says solar system. So that would mean we would be measuring on a first order measurement would be measuring orbital velocity, but we don't measure that. So that means the sky is moving. That's what all these measurements are measuring. I haven't even said that yet. The sky is moving, and that there's an ether, the material medium that everything is in, that's moving. It's a relative motion issue. These people think that this relative motion is the opposite of what it is. But the ether is moving. We are stationary. The height effect. The velocity of wave propagation depends on the height above the Earth's surface. That is stipulated by the Earth's surface interaction with the viscous ether stream, material medium responsible for electromagnetic waves propagation. The space effect. This is the periodicity of the daily periodicity. The velocity of wave propagation changes its value with a period of one stellar day. That is stipulated by a space galactic origin of the ether drift, the medium responsible for electromagnetic waves propagation. Thus, the height, astronomical coordinate, of the solar system movement apex will change its value with the period per one stellar day, as well as for any star owing to the Earth's daily rotating. Therefore, the velocity horizontal component of the ether drift and hence the velocity of electromagnetic wave propagation along the Earth's surface will change the values within the same period. The hydroaerodynamic effect. The velocity of electromagnetic waves propagation depends on movement parameters of viscous gas like ether in directing systems, for example in tubes, that is stipulated by solids' interaction with the ether stream, material medium responsible for electromagnetic waves propagation. So, we covered this, kind of. I mean, we all know about this. Hopefully none of us are denying the fact of this, because even the Earth rotation people say that. Although they try to... I won't go into that. Height effect. So as we go higher at altitude, we see a difference in propagation rate. Interestingly, Thomas Roberts, absent from his analysis, completely absent, but corroborated by Miller and corroborated by Galev via experimentation, not via Fourier transform. Huh! Wow! We can do experiments. We don't have to just Fourier transform some dude's data from 100 years ago and then poop all over him. Pardon my French. But we can just do experiments. Anyways, so then there's the space effect, blah, blah, blah. We got into all that. Let's go to the final thing to talk about here, which is the hermetic metallic chambers. Because we've talked about that a few times. And if you talk to some glober, you talk to somebody that believes that the ground beneath their feet is in motion, they're versed on this, which nobody is, but you find the random crazy person out there that's a heliocentrist that is actually versed on this. They're gonna tell you, oh, they've measured that 30 times. They measured it 30 times, Miller, and Miller was proven wrong every time. But Miller said back in the 1920s, hey guys, don't put it in a metal shield. It ruins it. Literally you don't get a result. So just stop doing that. But they're like, oh, let's just keep putting in metal shields over and over and over and over again. Hey, guess what? No result. Relativity, good. So they just keep doing that. And they got away with that for the last 80 years or whatever, or 100 years. And Yuri Galev, about 20 years ago, came along and said, no, you guys, did you maybe read what the acoustician had to say? The guy maybe did understand the ether. I don't know. So, let's just look at this metal shielding thing, because we can do an experiment. We can use experimentation. So, let's come up with this design. Actually, let me pull up. I have a picture of this. Here we go. Here we go. So this is the portion of the interferometer running through a metal shielding. And there's the man himself, Yuri Galev. So I just thought this picture was kind of cool. But in the paper, they actually have a diagram. I didn't mean to do that. So what they did was they shot... So you saw the metal shielding that was going around one arm of the interferometer. Where did that go?
I think you scrolled right by it.
Did I?
Yeah,
there it is.
Yes.
Yeah, here we go.
Yep.
So as we see here, we have an interferometer set up. We've got the light splitting here. So we've got one light wave going this way, one light wave going this way, and then a mirror directing them back into each other to recombine, where we can measure a fringe pattern. But we have the metal shielding, as I showed you right here, and then we have a fluid stream going across. So there's the larger level picture, the overhead image of what's happening. And then here's kind of a more specific showing that they have the metal shielding here, the light wave is going through here, and then the fluid is going to go across it this way. Now, what they measured was the translation of motion here. This laminar flow hitting the metal shielding is measured. There's a portion of that laminar flow that is measured within the metal shielding. So right there, crazy ether effect in my opinion. But specifically, what this allowed Galev to do was experimentally, so he would turn the whole interferometer, so this vector of the fluid would change, And as that vector change, wow, it's almost like he learned something from Miller. Miller understood that you have to do a bunch of data points along the vector change because that's how you get the most data. And even Thomas Roberts admitted that that was very clever of Miller to do that. But anyways, I digress. As this fluid stream is coming across here and you turn that, you can get a measurement of laminar versus turbulent flow on that fluid stream and the translation of that motion into the metal tube, and you can deduce how much of the and as you turn that fluid stream up at each data point or each vector point, you can then run it to its almost trending towards 1 point and find the viscosity essentially of the ether, or how much of that translation is making it through the metal tube. And this here is, basically one of this is like the heavy lifting equation, and they're using what's it called? The Poiseuille's parabola and Bezel's functions to describe the cylinder and to do the fluid dynamic math for the laminar versus turbulent flow. And it's interesting, they're doing fluid dynamic math on ether. But in any case, so, that's that. Essentially, like, he found you can't do it. You're going to screw it up every time. He let me find him laying it down. It can be suspected that solids, dielectric metals, etc., at interaction with the ether stream render major ether dynamic resistance. It clarifies the interferometer test results that the tube made of dielectric can execute the same directing system role for the ether as the tube made of metal. So it can be a dielectric insulator or it can be a tube made of metal, but it's going to have a system role directing the ether. And the ether stream property to pass aside obstacles could cause unsuccessful attempts to detect the ether drift with the devices placed in metallic chambers. So that's pretty much that. I don't think there's much else to cover on any of this topic. Let me just check here. Yeah, there's that. So that's everything I have to present. We can open the floor if anyone has anything they want to add in here.
What a good job dissecting that nonsense, dude. It's almost as if, how they think if they take Witsit down, flat Earth will die? I think if they take Miller down, then the whole ether dies.
And that's exactly why I got angry and jumped on this, because I don't want them poisoning that well or whatever, That's what they're trying to do.
Well, Miller's probably the strongest, and did most experiments, made the most measurements, but there's so many others that no matter what you do to Miller, it doesn't matter. You can't possibly take down all the people who are doing this work to show the evidence. Like, it's insane. So it probably, because they only ever heard Miller, because we talk about Miller, so they were like, haha, I'll take down this guy, discredit him, and then you'll have nothing. Nope,
well, and,
a whole body of scientific evidence.
It's like there really are a ton of papers out there about his work, so and most of them seem to be, they kind of corroborate his analysis. They kind of agree with his analysis, so, of a second order periodicity.
Not to mention there's many other people doing different measurements, different variations and experiments that all found the same thing. So it's like, I don't know what your goal is here, guys, to try and discredit this, pump out this one paper to discredit. I don't know.
Yeah. Anyone else have anything they want to throw in before I close out my stream?
No, that was a great analysis, man. Well, well said, and really appreciate the breakdown, man. Just
my pleasure.
Going through it all in a cohesive way, showing the first order measurements, the separation between a first order measurement, the second order interpretation. Huge distinction here. Like, that's how they've got us wrapped up in a paradigm that doesn't even exist, lads. So
I'm going to close out by playing the promo.
They went to go and measure
Tuesday.
Oh, awesome. Hell yeah.
So let me share that if anyone wants to watch that along for that real quick. All right.
The motion of Earth. The title of the paper is On the Relative Motion of the Earth and the Luminiferous Ether. It's not that they were looking for the ether. They already knew that there was an ether, they were utilizing that concept to make a measurement of relative motion.
First-order measurements are direct observations. These measurements are objective and can be directly recorded using instruments.
Second-order measurements are inferred or calculated. These abstractions can sometimes provide deeper insights, but rely on a proper understanding of the underlying first-order measurements.
My bad, I was muted on my stream. I apologize. Anyone tuning in, thanks for listening. Appreciate it. X, YouTube, Rumble, Kick. I know there's a ton of listeners on Kick. You guys are awesome. Hundreds. Just kidding. Zero. But yeah, thanks
Shout
for
out to the
tuning
Kick
in, and I'm
lads.
going to close my stream out. Take care, y'all.